When the ice recedes, shallow shorelines explode with biological activity. Insects hatch, baitfish spawn, and predatory fish move in to feed on the abundance. In early spring, lakes are isothermal. Because the water temperature is uniform from the surface to the lakebed, cold water species like trout roam across the entire basin. But as the calendar pushes into July and August, the surface water absorbs immense amounts of solar radiation, causing temperatures in the upper column to spike. To survive the heat, trout abandon the shallow flats and dive toward the dark abyss, vacating the upper layers of the lake. These deep-water fish do not enter a state of dormancy or stop feeding during the hot summer months. Their movement is strictly physiological. Trout remain active, but they are pushed into predictable holding zones by the physical stratification of the lake. To find them, we need to map the mechanics of the thermal squeeze, locate where that temperature gradient intersects with physical rock, and deploy tactics designed for extreme depths. Success in the midsummer depends on identifying the specific depths where temperature and oxygen levels meet the trout's biological needs. A trout is a biological engine built for cold water. Their metabolic efficiency peaks within a highly specific window, operating at its best between 50 and 60 degrees Fahrenheit. This chart maps a cross-section of a deep summer lake, tracking both water temperature and dissolved oxygen by depth. The top layer, the epilimnion, holds plenty of oxygen, but temperatures here climb well past the 60-degree mark, inducing physical stress in trout. The deep bottom layer, the hypolimnion, is cold. However, decomposing organic matter on the lakebed consumes the oxygen, turning this zone into a hypoxic environment where fish cannot survive. Between these two hostile zones lies a transition layer, often only 3 to 5 feet thick. This is the metalimnion, or the thermocline. Here, the temperature drops rapidly below 60 degrees, while oxygen levels remain high. Cut off from the hot surface and the oxygen-depleted bottom, cold water predators are forced to occupy this specific layer. Biologists refer to this narrow habitat restriction as the thermal squeeze. The thermocline acts as a strict biological boundary. Locating its depth on a sonar unit eliminates 90% of the lake's empty water. While temperature dictates the depth of the fish, changing barometric pressure alters how they hunt within that specific layer. High atmospheric pressure compresses a trout's swim bladder. Simultaneously, the clear skies associated with high pressure allow intense sunlight to penetrate deep into the water column. Under these bright, high-pressure conditions, trout become wary. They press tightly against submerged timber or boulders, and their strike radius shrinks to a few inches. When a weather front moves in, atmospheric pressure drops and clouds block the sun. The reduced pressure relieves the tension on their swim bladders. With the dim lighting masking their movements, trout detach from physical cover and roam across longer distances to intercept prey. The temperature identifies the depth of the fish. The atmospheric pressure determines how precisely the bait must be presented. Finding the depth of the thermocline provides the vertical coordinate, but predators also require a concentrated food supply. Look at this 3D model. Instead of a line on a sonar screen, visualize the thermocline as a horizontal plane slicing through the entire underwater geography. When an underwater mountain rises from the basin and its peak touches the depth of the thermocline, it creates a unique biological intersection. This same intersection occurs along steep drop-offs, known as break lines, or saddles that connect two separate structures. These topographical features act as physical barriers. When baitfish navigate along the thermocline layer, they collide with these structures and are forced into dense, concentrated groups. Trophy trout utilize these geographical bottlenecks as ambush points, pinning baitfish against the submerged rock walls. The most productive deep-water coordinate is the geometric intersection, where the temperature plane meets physical structure. Targeting these ambush points requires a shift in gear and rigging. As a trout grows, it undergoes an ontogenic diet shift. Once a fish passes 12 inches in length, the energy required to hunt tiny insects outweighs the reward. To maintain their body mass, they become piscivorous. They survive by eating other fish. To trigger a strike from an apex predator, you must deliver a high-calorie offering. Small nymphs are replaced with large minnow and baitfish profiles. Standard casting often fails when the target lies 40 to 80 feet deep. To reach these bathymetric intersections, anglers utilize vertical delivery systems. This schematic shows a three-way swivel rig used for deep trolling. A heavy weight tied to the bottom maintains contact with the topography, while a lighter leader trails behind, keeping the bait suspended within the horizontal thermal layer. When fish are pinned tight against steep drop-offs during high-pressure days, trolling moves too quickly. Anglers drop heavy metal blade baits vertically from a stationary boat, jigging the lure directly inside the intersection zone. Heavy deep-water hardware is a tool used to hold a bait at a specific biological coordinate. Deep-water trout fishing is an application of ecology and geometry. By calculating the temperature and oxygen band and mapping its intersection with physical structure, you can deliver a high-calorie bait directly to the fish. Aligning a trout's biological engine with the physical geometry of the lake makes their location predictable.